All right. So what we're going to be talking about right now is stereoselective directors. All right. We've already learned with our electrophilic addition reactions or our alkene reactions that there are certain stereoselectivity additions that we see, right? We've already seen that there is syn addition, there's anti-addition, or what I like to say is both, right? There's three possibilities. And there's even that fourth possibility of not applicable. But what we're going to be talking about today is these three possibilities and how having a director on your molecule can really determine the choices. So as we know with syn is that both of the groups are on the same side. Anti, if one of them is on the wedge, the other one must be on the dash. Or alternatively, if one is on the dash, the other one must be on the wedge. And both is just where the product is completely non-selective, okay? Where it does not matter what kind of product what kind of stereochemistry is there, all four are possible options, okay? Now, just by thinking about this, which of these three possible kinds of stereoselectivity do we think is going to be most affected by directors? And select all that apply. And if you think that it's going to be syn and anti, you'd be correct. We don't really care about what happens to this because it doesn't matter. Just because we have a director on there, it doesn't really affect what's going on. Maybe we get one choice a little bit over the other, but mostly because all of these reactions usually proceed through a carbocation mechanism, carbocation intermediate, we generally do not get any sort of direction that tells us what the product is going to be. Versus these guys are very much sensitive to what kind of direction might be forced on the molecule already. So let's take a look at an example. So let's say that we have this nice cyclohexane. Let's see if I can draw a nice one. And I want to put my double bond there. And, let's say that there is a good old methyl group that is on the wedge. Okay. Well, let's take a look at what our reaction would be. Let's say that we're doing Br2, which already we know is the halogenation reaction. We know that this reaction proceeds through that cyclic halonium intermediate. We know that its regioselectivity doesn't really matter. Both get an X. And the stereoselectivity is anti, right? This is all information that you should be able to just recall immediately based on those reactions we did in the last video or even from the alkene comparison chart, okay? And before we take a look at how this stereochemistry is going to direct what's happened, let's just predict the product, okay? Well, we know that our product is going to be this structure. And we're going to be adding a BR to both sides, right? So we know that our product is going to be, a BR is going to be on that guy and a BR is going to be on that guy, right? And so the question is, well, which one is going to be on the wedge and which one is going to be on the dash, okay? And this is where knowing the mechanism is going to be really, really important for being able to distinguish what happens with these stereochemical designators, okay? So let's take a look. We know that on the first step, what happens is that the BR is kind of hanging around with its buddy BR. All right. We know that the double bond is partially negative and that one of these bromines is going to be partially negative while the other one is partially positive, right? Because what happens is that the Br and the Br are the same electronegativity, right? But what happens is that as they're doing a tug of war, back and forth, back and forth, back and forth, back and forth, one of them will grab onto the electrons for an instant, which makes it slightly more negative, which means that the other one is slightly more positive, which also means that our double bond will be attracted to that slightly partial positive charge and reach out and grab it. Okay? This will kick off our bromine. And the product that we're left with is a bromine that's going to be straddled between our two carbons involved in our double bond. And remember that this is our cyclic polonium intermediate, right? This ringed up bromine is involved in a ring, so it's cyclic. It's a halogen, and it's going to have that nice old positive charge, okay? The question becomes, which side is it going to form on, okay? Because if that stereochemical designator wasn't there, we know that it could form on the top or the bottom, right? If it wasn't there, this bromine will hover in and be like, okay, well, which side is less hindered? Oh, they're both equally, so I can go either to the top or the bottom. It does not matter. Okay, wedge of the dash does not matter. But what we see going on in this molecule is that we have a nice, tall methyl group. And so this bromine, when it's being attracted, when it's being grabbed by these two carbons, it's going to be like, okay, well, which side is less hindered for me to go to? And what we see is that 100% of the time, the bromine goes to the opposite side as the methyl group. And this is what we mean by a director, is that it's going to the opposite side of our stereochemistry because it is a less hindered side. And so we form that nice cyclic polonium intermediate right on the bottom of the molecule, right on the opposite side. Okay. Now, what we could do is we can, modify our nice diagram. And we can see that, oh, now we have that bromine stacked on the bottom. Now, what I want you to be aware of is that if we have, if this is the size of carbon, for example, then, maybe this is the size of bromine, okay? Bromine is huge compared to carbon, which is why if we can see which side is now hindered. Well, technically both of them are hindered, but which side is more hindered? Oh, it's the bottom side. And so what happens is that when the leftover bromine, which we know is this guy right here, it's now a nice good old Br minus. I'm going to put, maybe I'll change this so that way we can see it in pretty colors. What we see going on is that this bromine is going to attack one of these carbons. And based on our knowledge from last time, we know that it's going to attack the more substituted side of the double bond, which is going to relieve this bond between the more substituted carbon and our cyclic polonium ion. And what comes out of this is going to be our bromine that's attached. But the question is, what side is it on? And so what we can do is we can do another analysis of the hindrance. And we can say, okay, here's our bromine. And it's trying to decide, does it want to fly by through the bottom or does it want to fly by through the top? And so it says to itself, well, which side is easier to access? Imagine that this thing is a plane. And which side is easier for the plane to fly by? Oh, it's the top side. So this bromine is going to come in and attack from the opposite side of the cyclic polonium intermediate. And what we find is that we have this nice wedged bromine on the more substituted side, and we have a nice dashed bromine on the less substituted side. 100% of the time, no ifs, ands, or buts. Okay? So when we're talking about stereochemical directors, what we're describing is the ability for the director to force what the cyclic colonium ion forms on first, which then forces the second bromine when it comes in. Okay? Let's take a look at another example, shall we? Well, let's say that we have this molecule. Let's say that we have this molecule. And once again, we're going to react it with Cl2, and we'll leave it at that. And the question becomes, what is the product going to look like? Okay. Well, we know that this reaction is going to put a chlorine on the two carbons involved in the carbon-carbon double bond. And the question becomes, what is the stereochemistry going to be for those two chlorines when they get added? Okay. So let's do a little bit of a hindrance analysis. Okay. And already what we can see is we have one tower on the top and we have two towers on the bottom, right? Talking about methyl groups here. And so we know that this chlorine bond is going to come walking up. We know that this double bond is slightly negative, whereas one of these chlorines is going to be slightly positive. And the double bond is going to do a double-handed grab, a two-handed grab, and grab one of these chlorines, which is going to kick off the other chlorine. And we're going to end up at our first intermediate, which should be the cyclic colonium ion. So our double bond has degraded into a single bond, and we're going to be adding these two bonds to a chlorine. And the question becomes, all right, what side is the chlorine going to form on? So we can go back to our diagram, and we're asking ourselves, which side is the easier approach for our chlorine? Well, it's most likely going to be the top, right? So our chlorine is going to be forming on the wedge. Okay. We know that we're going to have this leftover chloride ion. And this leftover chloride ion is going to be like, oh, damn, I know that I want to go in and attack the more substituted carbon. All right. This chloride ion is like, okay, I know that I'm going to be attacking this thing with all of my might. Okay. But the question becomes, which angle is it going to be coming from? Is it going to be coming from the top or the bottom? So we go back to our diagram. And what we see going on is that we have this massive chlorine on the top now. And what we see is which side is less hindered for our chlorine to come and approach. Imagine this thing is a plane. Kind of looks like a shoe. And the chlorine's saying to itself, okay, which side is less hindered? Well, on the top, we have a methyl group and a massive chlorine. And on the bottom, we just have two little methyl groups. So which is the easier approach? It's going to be from the bottom. And so what our product will look like is we're going to be coming in from the dash side. So we know we're going to be relieving that bond as well. I forgot to draw that in. So we know that chlorine is going to be coming in from the dashed side. We're going to relieve this bond here with the halonium ion, which is going to put it on a wedge bond. And boom, this is our product, right? No, don't forget too that if we have something on a dash here, we have to make sure if there's any other kind of group that we're showing that it's the opposite kind of bond, right? So this thing, this methyl group that was already included in the molecule should now be on the wedge, okay? So don't forget that if you're adding something that already includes a methyl group or some sort of a substituent already, and we're going to be changing the stereochemistry of that, we have to reflect that change in the stereochemistry already. Okay.